cross-section in here. So I think this is the picture I found on the internet. So to explain what a cross-section is, so there is a solid, the cylindrical can, like a food can in there. This is one cross-section. Maybe to you it's almost like horizontal. If you cut it like this, you can see how it cuts this can and giving you this type of a sectional cut in there. It becomes two pieces if this is really a razor, and if you cut it like that, and that will be the face inside there. Does that make sense? If you cut this one with like this, and then you can see that in the slanted cut, it's not really a perfect circle. You can experiment it. It becomes a little ellipse shape. And that's a cross-section talking about. If you cross it like this, cut it like that vertically, and you can see the cross-section you get is a rectangle. Right? So in this way, it really hides the nature of this thing. You have if you keep cutting it like this, you have a bunch of rectangular shape, right? But they're all put together into the cylindrical shell. If you have a collection of these circular shape, you can easily imagine that must be the circular cylinder. So this is what we mean by cross sections. All right. So the method uses this cross section. That's what that cross section is about. And under the cross section, there is a circular cross section and non-circular cross sections. Today we probably spend most of the time in the non-circular cross section. And circular cross section after that is mechanical and easy. It is just a little bit confusing with the cylindrical shell, but it's once you get that, is, if you set up axis and variable correctly, and it's not a problem. But students find a non-circular section a little difficult. And that's what we're doing today, and we do that. We manage through that, but students that think that's all and completely forgot about non-circular. That's going to be on the test. I guarantee you, non-circular section method is going to be on the test. Many students misses it. All right, so let's see the next part, and let me explain this one first. So we're focusing on the method of cross-section, and especially non-circular cross-section. If you cut it, that section is not a circle. All right? So let me show that picture again. This one was a circle, right? This one is a not circle, and that one is a not circle, correct? So we're talking about these latter two kind. We have information about this cross-section. It's not circle, and we want to see that. So first thing we do is that not just thinking about the cross-section. Remember, you have to understand this first part is very important. Axis of cross-section. You have to determine which one is going to be my axis of cross-section. If this is our problem, and if you can decide axis of cross-section, and this cross-section is really nice, you can see the cut is always the same shape, right? So it seems like very simple. But this one is changing, and this one is ellipse and more complicated. It seems like that's the best cut. So maybe there is an axis of cross-section you can choose so that your cross-section is regular and very easy to understand. That's the best axis to choose. So that's what we're talking about here. You have to have this line that's called axis of cross-section. That is usually your choice, best choice. And the next thing is that you actually cut in a random place. And if this is regular, you can control it better. The key thing is that this cross-section is supposed to be perpendicular to the axis of cross-section, right? Let me go back and tell you, show you this picture again. If it is like this, if a cross-section is like this, how would you describe the axis of cross-section? Vertical, horizontal? Looking at the first picture. Axis of cross-section, vertical, horizontal? Horizontal will be this line, right? That doesn't quite look like a perpendicular to the cross-section. It's a parallel to the cross-section, right? So axis should be like this, the vertical, so that cross-section is really perpendicular to the axis. That's the key, right? You have to keep that relationship clearly so that your volume is correct calculation. If you're a little slanted and cut it, that doesn't tell you the right volume. It has to be perfect perpendicular. That's a bit mysterious. Why is that? But that's something to think about. That little error introduced by slanted axis is actually the first kind of error. Add up to 1. Remember that part? Triangle thing. So that is the little error. So you have to be perpendicular. That's the important part. What about this one? If it's cross section how would you describe axis of cross-section? A little bit slanted coming out of here, right? If you have taken calc, well, it's a calc 2, it's calc 3 that we have a machinery to describe that. What about this one? Axis of cross-section is horizontal this time, right? Like pointing out like this, but it is, vertical like this, and is compared to that is horizontal. That's the axis we're talking about. So if you cut that perpendicularly, and the area of that cross-section area is usually denoted by AZ. What is a Z? Is the name of this axis of cross-section label. Right?
It's the function used to describe the area.
Right. If you take the cross-section, you can think about the area of that face, which is flat, right? Because you cut it. And that area is represented by A with the parameter Z. Again, what is this parameter Z? The position and the axis of cross-section, right? So that number. Each location, you take a perpendicular cut. What is the area? And here, you can see AZ is a constant function. Would you agree in the first picture? AZ is a constant function. Doesn't matter what your vertical position is. It is always the same area, right? It's a constant function. Doesn't change. Here, this area, right? If you locate that a little bit above, different location of axis cross-section, isn't that going to be exactly the same thing, right? Area is the same, so constant function. Right? AZ is just a number. It doesn't depend on Z.
So a non-constant function have two variables, one variable changing, the other variable?
No, there is a variable. AZ, in this case, AZ, this is always a constant. Doesn't matter Z is 0, Z up here is 1, 0 up there is 3. The area is always, it is not depending on Z.
What's an example of a non-constant function?
Z. Z squared?
Oh, so it is linear.
That's not linear. Yeah. Linear is not the right term.
So linear, okay, never mind.
Yeah. It's a constant term versus non-constant term. Right? Linear is just AZ plus B, that's linear. Z squared is not linear. One variable, two variable. How about this one? If I slant this parallel movement of this cross section like that, or to that direction, do you think it changes cross section?
Yes.
Locally it doesn't. If you move it a little bit up here, I don't think it changes. However, if you cut it above in the top part and it becomes wedges, it changes, right? So locally constant, but globally eventually it changes, right? So that's not very good. How about this one? If you keep pushing back and forth this cross section, you see that area is not changing at all, or changing. It's changing, so it's a non-constant function, right? The area of AZ in the number, depending on Z, that's what that AZ is, right? Okay, then you have to formulate that, and it is saying the volume is the integral of the cross section, right? So without an example, I went through this abstract discussion, so some of you might have understand, and some of not. It actually makes no sense if I talk like this. So we have to look at examples. So, but let's formulate with a better picture first. This is just random cross section. So here's a good picture. Let's say this was solid, and we wanted to compute the volume of this one. That's our goal, and we want to analyze this one. And first thing we have to do. What was the first thing we have to do? Axis of cross-section. You have to determine the axis of cross-section. If you look at it like this, if you put the axis of cross-section vertically like this, or the other way around like this, you can imagine it is more irregular than this particular cross-section they introduce here. Seems like there's some regularity in the shape of cross-section along this x-axis in here, right? So that line here is axis of cross-section, and if it is sitting inside xy plane, you can name it. This is a position 0, and that's a position 5, x equals 5. Or this is x equals 0, that's a negative 5, and it's a positive 5. If it is a symmetric across that number, things like that. So that's your choice, where you would locate the actual coordinate system after you decide this is going to be axis of rotation. What was the next thing? You have to understand the area part, the actual cross-section. So do you agree that this plate here is a perpendicular to the axis of cross-section? Seems like in this 3D picture. So that's the important part you have to understand. Here's the axis of cross-section. That is a perpendicular, actually, face that cut in here. So that's the face right there, right? So area of that one seems like it's a part of that formulation. Why is that? It is the following idea here. You can see they extended it perfectly parallel to axis of cross section. That's the idea. You can't just randomly thicken it like this. This direction must be perfectly parallel to axis of cross section and thicken like this. And you can see this portion escaped the volume a little bit. That portion is a little underestimating and all that. So it's not perfect measurement, but it's going to be good enough approximation, and that has to be justified, but which we won't. It's too much work for us. So we'll accept that if I calculate the volume of that thin slice and here and there, and that'll correctly approximate the volume. Does that make sense? All right. If it is a parallel like that, axis of so that's one shape we decide to go about, like this one, and extend it back and forth a little bit like that. How we're going to compute the volume of it is that because it's a cylinder with this parabolic top and bottom, exactly the same copy, the area of this side times the height or the width, that is the volume of it. So let me show you the picture of other cylinder. Usually we're familiar with the circular cylinder with a very narrow, small height. Can you imagine that thing? So here is the area here is usually pi r squared, right? If it is a circular top. If the height here is very, very small, like little h, what is the volume? Base times height. That is the volume of the cylindrical shape. Even if it is slanted like this, and is a pi r squared, if this height, the direct height up there is h, that the volume is the same, pi r squared times h. Not easily understood, but I think that one is usually introduced in the geometry course. What is the volume of a cylinder? Base times height. What do we mean by cylinder? Certain shape was keep continuing, copying, like you can imagine pentagon or star shape that can keep continuing like this to the bottom, an exact same copy like that. That's a cylinder with a star-shaped base and top, right? If you know the area of this guy times the height, that's the volume of this one. And that is the definition of the volume of a cylinder. So the very basic definition, just like the definition of the area of a rectangle, right? Have you ever questioned that? Why is 1 times 6 is equal to 2 times 3 if as a measure is the same? And is that a good definition or things like that? So you have to ask that question, but we're not going to answer that. But that's the definition, base times height. So here, the base is extended from our special cut. So area of that times height, that's the delta, right? So let me go ahead and formulate it here. That cut that we were looking at there, little slice of pound cake or something. Here's the area, and that place z is a of zk, the Riemann sum, right? Was that zk or xk? It was xk, sorry, that xk. Suppose we have that information. Given the location of x equals xk, we can calculate the area of this side. And how about the thickness? What was the notation for thickness? That is the direction of axis of cross-section. In Riemann sum, what is the usual this notation for the thickness? Delta xk, is that right? That's the x-axis, and we're chopping into smaller pieces. That's the Riemann sum idea, right? Although we're not calculating the area. All right, so what was the volume of this again? Delta vk, is that right? Volume of that little slice. Base times height. The base here is this side, area ak, a of xk, times what is the thickness or height? Delta xk, right? That's one slice. If you add them all up, we believe that measures the volume correctly. So they have a nice picture in here. So I'm showing again. How about that? That is actually the cut. If you look at each of the sides is perfectly flat and is parallel to the axis of cross-section. But if you do many, many times, we believe that Riemann sum is actually the volume. And that's a good definition for the volume of this type of thing. All right? So we're here. That's one slice. How do you add them all up? Volume must be correctly approximated by adding all these volumes like that. A of xk times delta xk, right? So how do you know it's a Riemann sum? Delta xk is isolated as multiplicatively, and everything else is written in terms of xk. Then it's a Riemann sum. right? So what is this approaching actually? V. Integral from A to B, where however you coordinated it, and this AXK changes to just AX, right? What happened to that delta XK? DX. But these are just the placeholder, letting you know how the Riemann sum actually looked like. But this whole thing represents just a single number, right? Make sense? All right. So what other things? How do you, anybody remember the regular right Riemann sum? What is a delta XK? Anybody remember the formula? B minus A, that's whole length, it chopped it into how many pieces? N pieces, right? That's the N pieces. That's correct. I got that B minus A. That's good. How about XK? That's a bit tricky. Starting from A, remember? Starting from all the way to A. Each step you go to how many units do you go in the next step? Which is really delta XK, right? So you go starting from A, delta XK, 2 copies of delta XK, 3 copies of delta XK, and so on. So K times delta XK is a formula. If you like, you can replace the delta XK with B minus A over N. So this is the detail of the Riemann sum. Okay? But this is the cool part of the Riemann sum, is there's definite integral, right? And there's no antiderivative, but what theorem connects this definite integral to antiderivative? Fundamental theorem of calculus. Definite integral going to antiderivative. That's FTC. All right? So we can calculate this quickly without doing the Riemann sum. All right. So what's the bottom line here? If you can handle cross-section area, multiply by delta z, and that's going to be the volume. But integral form is like this. Integral of cross-sectional area is volume, right? That's how you're going to memorize it. But why is that? Was just explained. So we really need examples. Here's an example. In the test, if you look at your textbook, they gave you nice pictures of the shape of a solid. However, in the test, it's going to given like this. You have to kind of analyze the shape of a solid. Maybe some of you would good an artist and then you can actually sketch it. But sketching the actual shape of a solid often not necessary, especially for test problems. There's some homework problems that 3D visualization skill is sometimes advantageous. But in the test, it's very standard, and you have to learn how to analyze the stuff so that you can kind of calculate the volume of this thing without actually being able to see that solid in there. So let's look at this problem. A solid has a base. That's one term that you have to learn that is not introduced. It's like flat base, something like that. So just like that one was introduced before, here, like this one has a flat base in there, right? If I give you a solid ball, that doesn't quite have a base, is it? The bottom part is just a point there. So that's what they mean by that being a base. Is bounded by the curve y equals x squared and y equals 2 minus x squared. So they describe the base. So let's do that. These are relatively easy graph. They can calculate y equals x squared, this one here. Correct? How would you describe 2 minus x squared? Concave up or concave down? Concave down. 2. What are you going to do with the 2? Shift it up, right? So 2 units up there and going down like that. That's y equals 2 minus x squared. Correct? So does that make sense? Bounded by these two curves. You see that curves there? So that's the basis. Above, toward to you, there's a three-dimensional solid coming out from that base. Does that make sense? There's something above here, but that's the base, if that's sitting on the desk. All right. So, for example, if I describe it like this, that's the base. Above it, there's some sort of solid on top of it. That's the base they're talking about. And next thing they talk about is that cross sections through the solid perpendicular to x-axis. So what is this x-axis? That is the axis of cross-section. Does that make sense? That is your axis of cross-section right there. So the plate is going to go through perpendicular to this one. So I'm going to extend the x-axis here. If I put the plate, how is it going to intersect this xy plane? That plate is going to intersect like that, perpendicular. But it's really a three-dimensional plate. Plane is penetrating through. That is a cut. The machine is keep cutting to the left, and eventually it's going to slice the solid, like that. Does that make sense? So we want to understand the shape of that, the cross section. So next thing is that the semicircular disc. That's what they're saying. So if you cut it somewhere here, you don't want to cut it here. That's outside the solid. You want to cut it somewhere in a random position. Is that right? Random position x here. If you cut it, that's going to generate this type of mark in the base. And you can see it's going to cut the base right there, whatever the solid is. Or I'm going to label that A, down there B. It's a good habit to have it. Always label it correctly. Label that is time A and B. That's only the base of a cross section, right? What's on top of this? They say the semicircular disc, right? On top of the semicircular disc. So if I rotate it around like this, A to B, so this is really a three-dimensional way. I just rotate it around and kind of look above it, and here, above that, there's a semicircular disc erected on top of it. So you have to take that one sheet of semicircular disc and put it on here and glue on top of it. Can you picture that? So here's the base, and here's a B, and here's A, right? And here's that line we're talking about, and I draw a little semicircle on top of it. So there's a base, and a perpendicular semicircle is glued on top of it. Does that make sense? So if I go back there in this picture, we have this information down here, and we put, instead of this parabola, I put over a semicircle shape there. Does that make sense? Okay, so I want you to look at it separated like this. You sketch the base in two-dimensional clearly so that you can calculate and control perfectly, and separately sketch the cross-section in here. So these two pictures cannot go together in two-dimensional places, but these two pictures fit into a three-dimensional picture, right? Just like I try to do it here. So what I was saying is that being able to visualize this shape is not that important to calculate and complete this problem. Just separate it. This is the base. This is a cross-section. Just make sure that how this one is glued onto that part, and that's why I labeled that A and B. Correct? All right. So what is the main variable here? Integral variable. X or Y or Z. This is the axis of cross-section. X is our main variable. Correct? Right. So let's go back to the problem here. Axis of cross-section, done. And we have to figure out the area of the cross-section in terms of what variable? X, in this case, X, right? Z represent X here. Make sense? All right. So X is given in here, and we have to calculate the area of this guy. Sketch separately. So what is more important to calculate the area of this one? Radius of the semicircle, right? So if it is not immediately available, just label it R right there. We're going to take care of R as a function of X. Everything has to be a function of X, correct? We'll do that later. Let's see. Do you agree that is not constant? It changes as X changes. If the cut is here, you can see that AB, that is that AB, right? And if I locate X equals 0 there, you can see that's a lot longer, right? And then this circle will have a lot longer diameter. That's what we're talking about. Does that make sense? Yeah. So name it, and what is AX? Somebody, what is the area of that cross-section? In terms of R, that's what I'm saying. Pi R squared, right? But divide by 2. So it's 1/2 pi R squared. Is that right? So write it then. And you understand R is actually a function of X. So now the second goal is that, okay, let's go ahead and write down this R as a function of X. I think the key thing is that AB is natural there before we actually go into half of it. AB is right there, right? So go back in understanding that A and B are corresponding to that. So do you think you want to calculate the x-coordinate of point A or y-coordinate of point A if you are interested in computing this length AB, right? Then half of it is R. So for that point A, you want to calculate y-coordinate or x-coordinate? Y-coordinate, right? Why? Because it's vertical. You want the distance between these 2 points. Correct? So what is a y-coordinate of that A? It came from that parabola, right? So 2 minus x squared is correct? It came from that parabola right there. That always confuses you. You have to follow, and there it is, 2 minus x squared. Follow the curve and label it. Label your curve always. How about the point B? Y-coordinate is B, there's x squared, right? So in this entire picture, you know A is always above, I mean the 2 minus x squared is always above than the other, right? So you know the correct order. So what is the distance between, this is usual standard notation, distance from A to B, what is it? 2 minus x squared, right? Minus x squared, so altogether 2 minus 2x squared is what? The distance of it here. If you locate your x over here, you plug in that x value there, which is 2 minus 0, and that distance from here to there is 2. If you locate your x over here, that distance here is this formula, 2 minus 2x squared. All right? Fair enough? So look at this outline. Go ahead and make this cut in the base. And separate the draw and draw the cross-section shape. And you can, have these two pictures. You can relate everything back together nicely. All right, so what do we want to know for AX? That's all we want to know, right? That A and that A is unfortunately different. So let me change the entire thing. I make the same mistake. PQ, right? A is supposed to be the area, right? So that is supposed to be PQ. Is that right? PQ, that's PQ. So about that. And there is a PQ as well. Stick to PQ. Changed everything? All right. So what is RX now? Half of PQ, right? So 1/2 of PQ, which is 2 minus 2x squared. Is that okay? 2 cancels. 1 minus x squared. We got that. The radius of that location and axis of cross-section, the radius of this semicircle we're looking at is 1 minus x squared. Right? So let's finally, what we really want to know is this AX, right? What is AX? 1/2 times pi times r squared, right? What is r? 1/2 times pi times 1 minus x squared. Good? Yeah, why didn't you not squared? Thank you. That's a squared. So when you integrate, I think you have to expand it. Maybe you expand now, right? Pi over 2. What is it? 1 minus 2x squared plus x to the 4th. That's the binomial expansion theorem. What's next? All right, let me show you that picture here. All right, we got axis of cross-section. When you compute the area of a cross-section, we did two things. Analyze the base and separately sketch the cross-section and see where it glued together. Then you can figure out AZ, all the problems in the book. All right? So we figure out AZ, right? Then what is the volume? Integral of the area is becoming the volume, right? So that's right. So that's the next thing. The volume is A to B that we don't know, but at least we got that AX part. So what is AX? You copy that one exactly, and it's ready to be anti-differentiated like that, right? So we realize that it's probably a good idea when you looked at the base shape, first figure out intersection points first, because that's what that A and B is supposed to be. So what is A and B? So I'm showing you the picture again, as you can see the whole thing. Leftmost point where the last bit of a solid is touched is this part here. That must be x equals a, right? And this part in here, that must be x equals b. We've been practicing computing the intersection points, right? Set them equal to each other and solve for it. I think let's guess it just to save time, but it's going to be solving polynomial equation. You can see that, right? So let's try 1. You get 1, 1. That works, right? If you just try 1, 2, and then hope we can do that in the test. Just guessing it and doing quickly. So you worked out A is -1 and B is +1, right? By inspection and by plugging in, and you can verify that our inspection is actually correct. So the rest is a simple integration, correct? Do you think you have any question at this point? What? Yes. That is correct. Right. Anything else? All right. Let's look at this outline one more time. I said this is a lot harder than the other ones, right? What were those? Circular sections, this is a lot easier. Non-circular section is a lot harder. But that concept is more important. So that's introduced first. All right, axis of cross-section, usually your choice. And area of a cross-section, separate the two, the base part and cross-section part. Know how to glue it. You'll be able to find that AZ. And last bit is easy. Just integrate that cross-section along the axis of cross-section. All right, let's look at other problems.